So, we would continue with this analogy and most importantly the application of analogy in solving real life problems, in problems where we have a prototype in which heat transfer is taking place. We would like to know what is going to happen without doing the experiments if a mass transfer operation takes place over such a device. But before we do that, let us quickly look at the thicknesses of boundary layers, the momentum, the mass transfer and heat transfer boundary layers in light of the analogy that we have developed so far. So, we are looking at the boundary layer analogies and we are looking at the significance of the numbers which we have come across. The first number that we have come across is Prandtl number, which is the momentum diffusivity. So, this is mu by rho divided by thermal diffusivity, which is k by rho Cp. So, the Prandtl number is essentially then a ratio of momentum diffusivity by thermal diffusivity, and it can be seen from the results of delta and delta T, that is the hydrodynamic boundary layer thickness divided by the thermal boundary layer thickness is equal to Prandtl number to the power n. And for a gas, since the gases are very well mixed, then for a gas delta T, the thickness of the thermal boundary layer would be equal to the thickness of the hydrodynamic boundary layer. But for a liquid metal, since the value of K is very large for the case of liquid metal, the thermal conductivity of a liquid metal is so high that the effect of the solid surface in contact with the liquid will be felt at a greater distance inside the liquid metal. So, if you have a solid plate and you have a liquid metal on top of it, since the thermal conductivity is so large, the thermal diffusivity is so large, the effect of the plate will diffuse to a greater depth into the liquid metal, and therefore, the point over here will sense in terms of temperature that a solid plate exists over here whose temperature is different that from the flowing liquid metal. But at this point, the hydrodynamically the molecule, the liquid molecule at this point will not feel the presence of the solid plate. So, for a liquid metal, the thickness of the thermal boundary layer is going to be much more than the thickness of the hydrodynamic boundary layer. So, the thickness of the thermal boundary layer is going to be large, since the thermal diffusivity is large. The thermal diffusivity of a liquid metal is going to be large, since the value of K is very large for the case of a liquid metal, whereas the thickness of the hydrodynamic boundary layer does not depend on the value of K. So, in cases of liquid metals, when it flows over a hot surface, the thermal boundary layer, the temperature front will propagate, will penetrate more into the liquid metal as compared to the momentum penetration of due to the presence of the solid plate. So, the thickness of the thermal boundary layer is going to be very large compared to thickness of the hydrodynamic boundary layer for the case of a liquid metal. On the other hand, if you have the case of a oil, for example, for any oil, this thermal boundary layer is going to be very thin in compared to the hydrodynamic boundary layer. So, we have two extremes: a liquid metal, high thermal conductivity, delta T is going to be very large compared to delta. For oil, with a low K and a large value of rho, the thickness of the thermal boundary layer is going to be less than the thickness of the hydrodynamic boundary layer. Similarly, we can get Schmidt number, which is nothing but the momentum diffusivity by mass diffusivity. So, momentum diffusivity by mass diffusivity, and delta by delta C, similar to delta by delta T. You can easily see that delta by delta C is going to be Schmidt number to the power n, and by combining these, the Prandtl number and Schmidt number, a new number has also been proposed, which is specially used for the case of simultaneous heat and mass transfer, which is called the Lewis number. So, Lewis number is, as I said, is used for simultaneous heat and mass transfer. It is defined as the thermal ratio of the thermal diffusivity by mass diffusivity. So, thermal diffusivity by mass diffusivity, if you bring in the momentum diffusivity in here both at the numerator and the denominator. So, what you see is this is equal to Schmidt number. So, this part is Schmidt number and this part is 1 by Prandtl number. So, this is nothing but the inverse of Prandtl number. So, Lewis number L E is equal to Schmidt by Prandtl number. Okay. And as I mentioned before, for the case of simultaneous heat and mass transfer, the thickness of the boundary layer, thermal boundary layer and the thickness of the concentration boundary layer, they are related by LE, Lewis number to the power n, and for most of the applications the value of n is taken to be 1 by 3. So, this is something which we already know, which are obvious, which can be obtained easily from the analogy. I have just jotted down these together so as to give you an idea of the relative thicknesses, the relative importance of momentum transfer, heat transfer and mass transfer, and how the boundary layer thicknesses of these three transport processes are going to relate to each other through the relevant similarity parameter, that is in terms of Prandtl number, Schmidt number and Lewis number. So, when you talk about hydrodynamic and heat transfer, it is going to be Prandtl number, hydrodynamic and mass transfer, it is going to be Schmidt number, and when you talk about compare between heat transfer and mass transfer, it is going to be the Lewis number. So, the importance and significance of these numbers, these dimensionless numbers should be very clear to all of you, and there are exceptional cases where this analogy in its current form will not be applicable. That I gave you examples of the examples of liquid metals, in which case the thickness of the thermal boundary layer will be very large in comparison to the hydrodynamic boundary layer, or heavy oil where it is simply going to be the reverse. The thickness of the momentum boundary layer would be more as compared to the thickness of the heat transfer boundary layer. Whatever I have taught in terms of the analogy, it is available in the book Incropera and DeWitt. So, it is there in Incropera and DeWitt, that I have mentioned at the beginning as a text, as a textbook for this course. So, the name of the book is Introduction to Heat and Mass Transfer. So, these analogies, the equations, the functional forms, all these are from Incropera and DeWitt. So, you take a look at it. It's very well described in the book, and I don't think you will have any problem in understanding, but if you do, please contact me, write to me, and I will try to clarify any doubts that you may have. So, now we are going to go into the last part of the course, the last few classes, where we are going to solve problems related to these analogies, related to simultaneous heat and mass transfer, and we would see that how the analogies will make our life a lot simpler. And there will be one more topic which I would cover probably at the last class, is the error function. The error function will keep coming back in the case of momentum, heat, mass transfer or many other problems. So, I would give you one or two examples of when the solution of a differential equation having a specific set of boundary conditions will be of error function type. So, you simply only have to write the governing equation, write the initial and the boundary conditions, and you can directly write what is going to be the solution for the process. Okay. And the use of that, so we will see that in the last class. But right now the problem that we are going to solve is it's again a problem on transport analogy. What it tells is that we have an irregularly shaped object. It could be of any shape. Okay, so and we simply have the same shape. I mean, these two are equivalent in terms of shape. I could not draw it properly, but you can get what I try to mean is they are irregular, but whatever be its shape, there is just a conversion factor, a scale factor by which you have increased it. So, this is object 1 and this is object 2, and you simply have made the size of the object a few times larger than that of object 1 while keeping the shape intact. So, if the shape was just a square, you simply made it a bigger square. So, this is what I mean when you keep the shape intact, but the sizes are more. So, you have to pardon my drawing, but what I am trying to show you here is this object 1, object 2, and let us assume the shapes are same. So, the irregularly shaped object which has an equivalent length to be equal to 1 meter, and it is maintained at a constant temperature of 100 degrees centigrade. So, this is maintained at 100 degrees centigrade and it is suspended in an air stream. So, we have air flowing over it with air at 0 degrees centigrade, which is flowing over object 1, and the pressure is given as 1 atmosphere and the velocity is 120 meter per second. So, the velocity of the air stream is also given. The air then what you do is you measure the air temperature at a point near the object in the air stream to be 80 degrees centigrade. So, somewhere over here you measure the temperature of this point and you find this temperature to be 80 degrees centigrade. The second object, in this case the length scale is instead of 1 meter, it is 2 meters. It is also suspended in an air stream. Now, both the air and the object in this case, so one is at 100 degrees centigrade and it is interacting with air at 120 interacting with air at 0 degrees centigrade. So, this is from 100 to free stream temperature of 0 and the temperature near the surface is given as 80 degree. That is the only information, experimental information that you have, and you have you know that the air is coming at 120 meter per second, its pressure is 1 atmosphere and so on. So, you have measured the temperature at a point and found the temperature to be 80 degrees centigrade. Now, in the second case where the length is 2 meter, both the air and the object are at 50. So, this is at 50 degrees centigrade and the air that blows, this is also at 50 degrees centigrade. So, these two are separate things. So, here you do an heat transfer experiment, but here what you have is a mass transfer situation. The airstream velocity here is 60 meter per second, and what you have a plastic coating on the surface, a thin plastic coating on the surface that you are drying by putting the flow of air on object 2. So, this plastic coating is to be dried by passing an air which is at 50 degrees centigrade. The temperature of the object is also 50 degrees centigrade. The molecular weight of the vapor is 82. Saturation pressure is provided. Saturation pressure for the plastic material is provided. So, P sat is known to you, and what you have to do is you have to tell for a second object at a location corresponding to the point of measurement of the first object, determine the vapor concentration and partial pressure. So, if this is your location which I call as A, there is a corresponding location over here which I call it as A prime. Your job is to find out, without performing any experiment, without performing any mass transfer experiment, what is the vapor concentration and partial pressure. So, at point A you measure the temperature, corresponding point is A prime on the scaled up object. In here, since both are the air and the object and the air are at same temperature, no heat transfer is taking place. But you have a plastic material on top of it which is getting dried, which is getting, so slowly you are having some evaporation from here in order for this plastic to be dried. So, you cannot measure the concentration, you cannot measure the vapor concentration because you do not have the tools to measure concentration, but you have tools to measure the temperature which you have done. Using analogy, what you have to find out is what is the vapor concentration and the partial pressure at point A prime. So, this is a classic ideal example. I think you have understood the problem. Now, I am going to go and solve for it. So, object 1 and 2. The first step is to calculate Reynolds number. So, what is Reynolds number for the case of 1? Kinematic viscosity 120 meter per second, where we have the heat transfer taking place, 1 meter is the length, and nu has been provided in the problem to be this much of meter square per second. So, it is 6.59 into 10 to the power 6. What is RE2? So, as you can see, these two are identical. So, the Reynolds number are same. The values of the Prandtl number which are shown over here, Prandtl number is 0.71 and the Schmidt number you can calculate. So, and see what is its value. So, it is provided that Prandtl number is equal to 0.703. So, this is for Schmidt number for the case of 2 where mass transfer is taking place is kinematic viscosity by DAB. These values are provided in the problem. So, you look at the value of Schmidt number and Prandtl number, they are equal. Since they are equal, Reynolds numbers are equal. So, if you go back to our fundamental equation and concentrate only on the heat and mass transfer part of it. So, if you concentrate on the heat and mass transfer part of it, you would see that Reynolds number are the same for the case of heat transfer and mass transfer, and at the same time the Prandtl number and Schmidt number are also same. So, whatever be whatever be the solution for temperature, so the functional form of temperature and the functional form of concentration, both in dimensionless form, must be equal to each other, because your boundary conditions are met, the equality of the boundary conditions are met, and this one REPR is equal to RESC, since RE1 is equal to RE2 and Prandtl and SC are almost equal. So, therefore, T star, the dimensionless temperature at given locations, must be equal to Ca star, X star, Y star. And how we define T star is T minus Ts surface temperature by T at infinite distance minus T s is equal to C A minus C A s by C A infinity minus C A s. So, the equality of dimensionless temperature and dimensionless concentration, which results because the Reynolds number are same and Prandtl number is equal to Schmidt number. So, therefore, the functional form of dimensionless temperature and dimensionless concentration, which are defined in this way, are the same. Now, as was mentioned in the problem, that the location for measurement was identical for between object 1 and object 2. The problem was to evaluate at a location corresponding to the point of measurement of the first object what would be the vapor concentration and partial pressure. So, when it says corresponding to a point of measurement of the first object, is essentially tells you that the dimensionless values of x and y, which are used to denote the point of measurement, they are identical. So, I can simply write this. So, once based on the analogy and thinking about the governing equations and their implications of the Prandtl number and Schmidt number and Reynolds number. So, since I have written this, the rest is pretty simple then. So, T minus T s by T infinity minus T s equal to C A minus C A s by C A infinity minus C A s. Now, I need to find out what is C A s, concentration of the species A at the solid surface, which should be equal to P A saturation divided by R T using the ideal gas law. So, this C A is the concentration of species A at the surface. The P A sat is provided as 0.0323 atmosphere. If we use the corresponding value of R, which is 8.205 meter cube, atmosphere, kilomole, Kelvin, and the temperature in Kelvin scale. The temperature for the case of mass transfer, it is 50. So, this is the concentration where, so CAS would be equal to so from here I can therefore write CA to be equals CAS plus the denominator CA infinity minus CAS times T minus Ts by T infinity minus Ts, just an expansion of that in terms of this. So, therefore, your CA is, this is CAS, value of CA infinity on at a point far from the wall. Temperature was measured to be 80 at that location, T surface is 100 and T infinity is 0 and Ts is 100. So, when you do that, you are going to get Ca to be equals 0.975 into 10 to the power minus 3. This is kilomole per meter cube. So, this T infinity, as you see in your in the problem, is 0 degree centigrade and Ts is 100 degree centigrade. So, this is the first part of the problem. The second part of the problem, the part B, tells you that if the average heat flux is 2000 watt per meter square for the first object, what is the average mass flux for the second object. So, we have already calculated the vapor concentration over here. So, now the next and I am sorry, the pressure, we have to also calculate the partial pressure. So, partial pressure would simply be equals P A, which is C A R T. The value of C A is already known, it would come to be 0.0258 atmosphere. So, an analogy essentially gives you the value of concentration and the value of the partial pressure without having to solve any mass transfer equations, any complicated equations. So, results obtained in heat transfer experiment can simply be projected to obtain results of a mass transfer experiment that you haven't done. Okay. So, this is one of the big advantages of this analogy, and now we are going to find out if the average heat flux is known for the first object, what is going to be the average mass flux for the second object. So, for this part, second part, we know that for one, Q double prime is provided as 2000 watt per meter square. We also know from Newton's law of cooling, this is H bar, average value of heat transfer coefficient, T of the surface minus T infinity, and in A double prime the mass flux would simply be equal to H bar m. In terms of concentration, this is molar concentration minus C A infinity. Since it is molar concentration, in order to change it to the mass form, I simply multiply it with the molecular weight. So, this is mass flux, molar concentration, molecular weight, and this is the average value of mass transfer, a convective mass transfer coefficient. From analogy, since Reynolds number of 1 is equal to Reynolds number 2 and Prandtl number is equal to Schmidt number, then I can simply write the average value of Nusselt, the average value of Nusselt number must be equal to the average value of Sherwood number. That is what is given by the analogy. So, if which I have discussed many times. So, if that is the case, then I simply divide this by this, and what I would get is n, and I can expand it a little bit more. So, H bar by H m, H bar m is equal to L 2 by L 1, which is L 2 refers to the mass transfer case, L 1 refers to the heat transfer case, times K by D A B. So, this is the relation from which I can obtain the unknown values, and then I divide N A by Q, and what I would get is N A double prime by Q double prime is equal to H bar m by H bar simply dividing this by this. So, therefore, my N A double prime the same expression over here, and now in this H bar m by H, I bring this one over here. So, in this, the value of Q double prime is known to me to be 2000 watt per meter square. L 2 L 1 is simply, the ratio would be 2. The value of K, DAB, CAS, CA infinity, TS, T infinity, and MA are everything known to me. So, I put this simply over here to complete the process, complete the calculation. This Q double prime is 2000 watt per meter square. This H bar m L2, L1. Right. You put all the values in here that you have calculated. So, after you plug in all these values, you would get Na double prime to be 9.28 into 10 to the power minus 4 kg per meter square per second, or if you want to express it in terms of kg moles by dividing it with the molecular weight, you get this value. So, essentially what you see here is the advantage of using the analogy. Since the Prandtl number and Schmidt numbers are equal and Reynolds numbers are also equal, since the length scale is length scale and the velocity, they vary in such a way that length times velocity remains constant, Reynolds numbers are also equal. So, the functional form of dimensionless concentration and dimensionless temperature would be identical, and by looking at the laws which would give you the mass flux or the heat flux, namely Newton's law of cooling and something similar to Newton's law of cooling, where the convective heat transfer coefficient H is replaced by Hm, where Hm is the convective mass transfer coefficient, and in the first case for heat transfer it is multiplied by temperature difference, in the second case mass transfer it is multiplied by the concentration difference. So, you can find out what is the ratio between mass flux by heat flux, and on the right hand side whatever you have, the only unknown here is the heat transfer coefficient based on mass and heat transfer coefficient based on just simply convective heat transfer coefficient. By analogy, everything this ratio is known to you, H bar m by H bar, and this would simply in one step by plugging in the values you would get the unknown mass flux which you would obtain on a similar surface when only mass transfer is taking place, no heat transfer takes place. So, by performing supposedly a relatively easy experiment involving heat transfer, measuring temperature, you would be able to predict precisely what would be the mass flux from a similar object without doing the mass transfer experiment. So, this specific problem highlights the utility of heat and mass transfer analogy. So, we would solve similar such problems which would also involve a little bit of thinking and modeling in the subsequent classes.